Today, Dr. Sergiy Shklyar will give a talk about resolution enhancement, probably using some statistical methods, I hope. Yes, you can start.
Thank you for introduction, and thank you for the opportunity to give a talk on the seminar. Today I will talk about perhaps there will be a little statistics here, such as estimates, but I will use some some methods of analysis, which such as rich regression. Multiframe resolution enhancement in a frequency domain. We consider the following problem. Let we can observe a series of images of equal or very similar resolution of the same scene, and we want to construct one image which has finer resolution. Perhaps I should have given the classification of different methods. So, sorry. We have several input images, and we are trying to construct one image of finer resolution. So there are different methods and different applications and different settings. That depends on whether we have one image or several images. We have several images. Whether we can evaluate the displacements between images or relative transformation between different input images from images themselves, or if we have or if we have some extra information.
Sergey, could I ask a question?
Yes,
please.
yes.
Just okay. Yeah. So what I'm trying to understand, you have one big image or some object, whatever. So your images, are you gluing them together? It's images of some patches of the picture, because you write like nx and y, knx and y, or you can get many different just pictures and shift only because of that. So I'm trying to understand. Can you go to the first slide? you put it nicely.
Yeah, yes, perhaps.
Yeah, 1 second. Displacement between images are parallel or near parallel. So it looks like it's small pieces, right? In other words, as physicists, what is nx and y size? What is k and x, k
No.
and y? Okay, sorry.
Well, I'll try to use this slide.
Uh-huh.
Um, we have several input images, and one of the same scene. One possible how these images could be obtained if is using a remote sensing with
Mm-hmm.
satellites. Uh,
Mm-hmm.
and uh, we we observe the same scene, and modern satellites have make can make several two
Mm-hmm.
series of two-dimensional images,
Mm-hmm.
and um, we assume that a relation uh, between these images is linear shift, ну, параллельный перенос.
Yeah, parallel перенос, and it's
Shift.
not exactly parallel
Shift.
shift. It could be some deformation. I understand that, but
Yes.
I'm just trying to understand, like satellite. It's maybe different views, maybe just different parts of the whole object which we want to recover, or it's just always the same. It just because we have move of
Uh,
satellite.
that does not this does not work with another flying objects with
Mhm.
it does not work with aircraft because and with
Because of resolution, yeah.
yes.
But pixels and x and y. Could you give an idea of the
Oh
order?
yes, yes.
Yeah.
We have an images. Then uh, we do then we try to get the intersection where
Mhm.
the common area that is on all of these images.
Mhm.
But and x times ny is the size of this common area.
Right, but n, x, and y, can you give an idea? It's 1,000,
Oh
2,000.
yeah, yeah. Yes. Uh, yes.
I
This.
just don't know level of resolution because then you use big K, right?
Yes, this can be of
Million even.
yes, this can be of order of thousands, maybe
Okay,
a few thousands or half thousand.
okay, thank you. Sorry, sorry, just
Mm,
wanted to understand.
mm. And we try to and using this and images we can we try to make one image but with smaller pixels. with finer, more
resolution. It's
yes,
not pixels. It make it a clear picture,
yes,
right? Because essentially you stack k observation over each pixel, right?
yes, yes.
And it's what I'm just thinking. And about noise, you have just noise which is due to you do not believe. I mean, you do not know how to describe. You believe that those shifts they are almost deterministic. So
Oh,
the main noise, and it should be kind of small. It's due to what is blurring or whatever, or warping. I don't know even English words. Definitely, I don't know Ukrainian for that picture, right? So shifts right now, it's almost like we believe it's deterministic.
oh, well, but perhaps not very unknown. I try first. I try to determine these shifts from images themselves.
Yes, yes. No, no, no. I understand. You're
Uh,
trying to use that information,
uh,
but yeah.
However, for that is that which I try to see, then uh, deformations uh, between these images was not different displacement over the field of the image was because of different elevation.
Hmm.
So
Because it's the same satellite you measure many times, but because of elevation, you physically you expect that it would be some shifts parallel, right?
mm.
Yeah, I believe so. Yeah, sorry.
And first I try to first I try to estimate the shifts between images. First we take two images and perhaps there are several methods which I which I um uh, implemented.
So
First,
you attempted a different high resolution resampling, you tried then low pass filtering and
uh,
some small shifting, right?
yes, first methods is I think it was patented by uh, well, it is known. It is and it consists of uses these techniques. First, images are resampled with high resolution
Mm-hmm.
um, using Fourier in the frequency domain. They
Mm-hmm.
were filtered. This was something like interpolation or approximation.
Right,
And
right. But what is image? Images are not very large. Could you give an idea? So, what does it mean? Not very large area
oh,
of what? Like.
well, in the second in the second method, um, images that are not very large was several hundreds
Uh-huh.
pixel each size.
So it's like
No,
a
100
small
is
matchbox, let's say, or even okay.
but I will describe this two last methods in more detail.
Mm-hmm. So finally, you use a hybrid low pass filter in state domain and some phase, or you call it spatial domain, and
Yes.
then some phase shift. Was it constant? I mean,
Yeah,
or it
yeah.
was some okay.
Yes, I will.
Yeah.
Here are
Sorry.
formulas.
I'm going to the ahead. Yeah.
Yes. First, I'm sorry for this notation. Uh, uh, First, let we have two images, y1 and y first and y second, and we perform a um, Fourier two-dimensional Fourier transform of these images.
Mm-hmm.
Yeah. Uh, Now we, sorry, I perhaps.
I'm
Oh,
sorry.
it's a good
You
idea
say
because yeah.
you say about maximizing, but what by what parameter?
Yes, parameter is delta x, delta y.
Okay. Okay.
Yes.
So
Sorry
so
for.
because shift you can transform into multipliers which kind of subject to I believe of optimization, right? Sergey, I
Uh,
guess Professor Maybrod is asking, are you maximizing what exactly? Theta 1, theta 2, right?
I am
Or
delta x,
delta?
delta y. These are parameters over which I am maximizing the
Okay,
functional
okay.
one.
But what is theta x theta?
Uh,
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 um,
First, uh, well, perhaps yes. Thank
because
you.
it's like Fubini. It's,
Yes.
at first you're maximizing, but you're taking into account that it's done for each frequency domain theta one, theta two. Okay, but it's
Yes.
different.
Uh,
Yeah.
uh, have, I'm sorry for perhaps I had to. Uh, we have two images,
Mm-hmm.
and uh, uh, delta x, delta y are shifts on one on x coordinate
Okay.
and y coordinate.
So,
I'm sorry, perhaps I had to.
okay. So you are shifting, and then you always use the same low pass filter to smooth and see maximization. Okay, it's complex.
Yes, thank you. Yes, this um, and this method works if image sizes are several thousands
Mm-hmm.
pixels um, each side, or perhaps half thousand is okay, and problem is because of boundaries of images,
Mm-hmm.
uh, and if images then there could be errors, and each these errors can be more than 1 pixel size. So I used a hybrid method which combines uh, shift um, shifting phases of the Fourier transform. Uh, oh, sorry.
But Sergey, can you explain, because here somewhere it's hidden already regularization. So at first
Ah,
you choose
yes,
right? Okay.
yes. Regularization is hidden in this
Yeah, it's what I thought. Okay,
multiplier,
thank you. Yeah.
uh, and this is h is a function which is an even function which is one around zero,
Mm-hmm.
and which is finite, and which is zero when theta, when argument is greater than one half.
So
Yes.
why one half? What a condition of that law passing?
This is a Nyquist.
Oh,
Uh,
Nyquist. Yeah. Okay,
yes.
got it. Yeah, it's what I thought. Okay, thanks.
Perhaps it's possible to use um,
No, but you need stability. It's what I was afraid that you wouldn't. It's a good idea to use some Nyquist criteria, because otherwise, low pass filter, if it's in rockets unstable, then kind of you predict the sound of the drum before hitting it. Yeah. So okay.
yes, and may excuse me, I'm very sorry, but I'm very sorry. Can I tell my mom that she's waiting for bus? Мама, автобус буде о 17:30.
Oh,
Зараз 17:23. I'm very sorry.
Okay.
no,
Very.
it's touching because it's personal connection with Kiev. You can hear.
I'm sorry.
Okay, you can continue.
Um, yes.
Okay, everything is
Well,
clear.
now we made two operators. One operator is a smoothing operator, or approximation interpolate
Hmm.
operator. When we perform it in the frequency domain, and we um, we make um, the Fourier transform finite. And the second operator is shifting operator,
Hmm.
we also perform in the frequency domain, and then we minimize the difference between images which are smoothed and
yeah, so the whole beauty of your technique, as I can see it, that all shifting in space, it's going into that exponent with the two parameters, and that's it. So it's obviously it's like, what kind of problem is it? It's non-linear optimism, or you would get finally just least squares. It's what I don't understand. Okay, sorry.
And in expression 2, the first summand is real, not complex.
Oh, he disappeared.
He disappeared.
Yeah. Now let's wait.
Maybe. Let us wait.
No,
And
it's fascinating topic. It just
yes.
I guess whenever
And
we walk in space and frequency, it's always a big problem.
and he wrote such an expression, and the summand should be real. He wrote something
Yeah.
minus.
No. Of course. For final sum, yeah. You're right. Yeah.
But
I'm
I
just
want.
curious how he solved it. It should be some maybe convex optimism. Yeah, it's some nonlinear optimization, but
Might be not convex.
it's what I cannot see immediately. I mean, if it's
And
yeah.
we have slides of his talk.
Could you pin him somehow to check? Maybe I don't know.
Yes, I will phone maybe.
Yeah. If it's yeah, just to check maybe.
sorry, I'm not sorry. I'm not
Oh,
sure
okay.
why someone. I think someone muted me. Sorry.
Oh, but we cannot see your presentation, right? It disappeared.
Yeah, I'm very sorry. I'm so
No, just share and that's it. I believe you know,
But
I also, yeah.
I'm.
it's okay. You have a lot of time.
Sorry.
Yeah,
Be quiet and it's okay.
yeah, yeah. And Sergey, sorry for interruption. It just
Yes.
I'm trying
Yes.
to, and it's actually we discussed with Professor Kukushik. You see the whole, yeah, okay.
How to see that the first summand in expression 2 is real, not complex?
First, yes. Oh, perhaps maybe.
This is real. You wrote a real part.
Well, maybe.
So now I am confused. What is real? What is Professor Kuku? What you're talking about? What is real?
SH of delta x, delta y, is it a real number or complex number?
No, it would be complex. It would be because you
Yes.
have exponent.
But it is written squared, maybe absolute value and then squared.
Maybe I have to check it in
Absolute.
I'm confused with this expression too.
No. Then you're right. You're right. Okay, I see. Yeah, it's no, but wait a second. It's operate in complex domain. You shift and then you consider. Yeah, it should be.
Should be modulus of complex number.
Absolute value. Yeah, sum of two. I mean, it should be norm of complex vector. Difference is a complex vector, and we're minimizing. But do we understand what is it? Yeah, it's a simultaneous optimization of the face, and yeah, it should work. It doesn't matter because in polar coordinates you still would minimize distance plus frequency, right?
Yes, I will check whether this expression is
I don't
real, this term.
Shift Y. White hat, it's not real, right?
Hello.
White hat is real.
Square for the absolute.
Sergey, the first Y, 1P or whatever, is it real? Y is real. No? No. I'm confused. Data. No, because transfer functions are not real. Yeah. So yeah.
Fourier transform is not real.
No, not for but H. What I'm saying that
H is real.
Transfer function, then it's just operate on a complex domain. So you are right. Yeah, you're. Oh, Sergey again somehow.
Again, it
Sergey,
disappeared.
can you hear us? Yeah.
Can you hear me?
You're right. It's, but then meaning. No, it's meaning that minimizing space and yeah. Okay. I see.
It is integral over space domain for
Correct.
different shifts.
No, but over there, of course, some hidden, I believe, complexities of discrete Fourier transform. What we're not talking about because it's a complex problem, but it's very interesting. Very interesting. Oh.
And this is can you see this?
We don't
slide?
see your screen.
Sorry. I have to share it again.
Yes, once again.
Actually, in Zoom I cannot see whether or not you can see my
Yes,
screen.
now we see.
Now we see everything. Yeah. Okay. Delta. Yeah, everything is complex. So you are minimizing distance between two complex numbers, and it's absolutely.
Perhaps here's some mistake because I use inconsistent notation. I'm sorry. Perhaps it's the slide, old slide.
Sergey, so what is the meaning of that anyway? Like what Professor Maiber, he asked about parameters, but what is the meaning of that optimization? So what we're optimizing? What is the meaning? It's not likelihood. It looks like it's some least squares. So maybe least squares both in frequency and space domain. I'm just guessing. So sorry, Sergey.
The delta x and delta y are displacements between two images x1, y1 and y2 on the x-axis and y-axis along the x-axis. So this,
yeah, physically it's clear. Yours that onto the picture. At first, you're shifting slightly. Then you're preparing, some going over some low pass filter, and you maximize quality of your picture. Then you do two operations, and you do it. It looks like at once, right? Because it's double sum.
double sum because perhaps it is easier to explain if we have not a two-dimensional picture, but if we have one-dimensional
Yes, yeah.
function, it would be easier to.
It is double integral.
Yeah, double integral. It's for Fourier.
L2 distance between Fourier transforms with weights H capital.
Yes, and there are summation of all theta where the over all the nodes where the Fourier transform is evaluated.
Wait a minute and show this formula once again.
Yes.
And theta 1 is the same as theta x, right?
Oh, yes.
And theta 2 is the same as theta y.
Oh, yes. Thank you.
Okay, clear.
Thank you.
Theta 1 and theta x is just the same quantities.
Sorry.
It is bad notation.
Yes. So it's not theta. Wait a second, I'm confused.
Under exponent, it should be theta 1 and theta 2 instead of theta x and theta y.
Is it? Wait a second. Yes. And then summing over all less than one. Okay. Oh my God. Okay. Now everything is clear. Yeah.
It is a sort of square distance between Fourier transforms.
Yeah.
Of
Nothing
shifted images.
Right. And we have separation, so we can use Fubini theorem or whatever.
Yes.
Okay. Over there it's correct. Okay.
And now, occasionally, we can have a lot of images. That depends on the imaging system, but occasionally we can have several 20 images or so. So we can drop some of the images, and there could be different ways how to do that. First, because the here should be a subscripts. First, because first we can check whether there is transitivity between shifts, whether the estimated shift between first and third images is the sum of shifts between the first and second and second and third images. And we can drop the images with where we have anomaly. Where
So it's your way of identifying outliers, correct?
Yes, perhaps of identifying bad images.
Yeah, so
Yes.
with some big outlier. But why how you choose that parameter of regularization 0.5? Why it's 0.5? It's not clear to me.
It is because of his age function, because his age transform
H,
function.
yeah, H.
It is zero out of this interval, minus one half plus one half.
Okay, okay. So
The second, ensuring that images that if we consider all shifts between images and the common grid, we try to choose a subsample of all images such that the fractional parts of the coordinates are form some net form some net on the torus. So second method allows us to if we have a perhaps I have to explain this second item. I have to return to the slide 3. I'm sorry. Oh, we have n input images and we cut some margins of the images. So after framing, these images represent images of the same area. However, because of finite pixel size, there could be subpixel shifts between images. And we have on this stage we have n images of the same size, nx times ny, and these images are shifted one relatively to another for distance less than 1 or 2 pixels at most.
Okay.
So on this second way of reducing the number of images, we just we try to ensure that that subpixel shifts relatively to the common grid should be nicely distributed on the torus without major gaps. And after we have calculated estimated the shifts,
Sergey, what is evenly distributed delta n? Why do you need? What is this assumption physically? I don't understand.
oh, well, perhaps I should have made more pictures.
Yeah.
Uh, if now we calculate by averaging, we calculate the subpixel shifts of the images against a common grid. This we interested now only in fractional part of the so this point and this point are the same, which differ by even number of pixels, which coordinates are differ by even by whole numbers. So and
Okay.
and the second the second way to reduce the number of pixels of images is to if we have images which shift displacements between which is almost um, has almost whole numbers coordinates, almost integer coordinates. Then we drop one of these images. Drop one of input images. And after we selected the preliminary after we selected input images, we uh, go to the main step, which is to recover the super resolved images, super resolved image, and we use Tikhonov regularization. Actually, Tikhonov um, regularization is um, is something like solving the perhaps over determined, perhaps underdetermined system of linear equations.
So, Sergey, what is your in penalty term? You have only one parameter. It's sigma squared n, right? That's it. You have only one penalty.
Or this one penalty term and this one.
So I'm confused. You have inverse that sigma matrix, but why it's not you're making with penalty term sigma like adding in other words you're adding some terms on of small terms over diagonal to make it non-singular, right? So it's only one
Yeah.
parameter.
Um,
It's only one parameter. It's called lambda. I mean, uh, you have your least squares value functional plus, then you are introducing penalty term for all, and it's the same for L capital images, and it's just one number, real number, which you have to choose eventually, right? Or
perhaps
showing that when it's small, it still would, whatever Tikhonov's theorem says. I don't care about it. Yeah.
mm,
No?
I think
Maybe I'm
excuse me, penalty term is the first I term or the second term, which is
I
we
think it's the second.
the second. Yes.
Yeah, so basically, you usually what people they would do, they have their, let's say, like penalized likelihood. You can write your likelihood, and you know that it's not likelihood because it's very flat. I mean, everywhere. Then you are trying to say, oh, it's flat, but it doesn't matter, kind of. If it's small degenerate or whatever, eventually it would be zeros on diagonal, right? And we would add first eigenvalue, it would be and we would add small number, and it would resolve our problem. I mean, I'm not saying, I'm just trying to say what rich regression is in statistics, right?
Um. No. Yes. For the system we use
Yeah, and it's
yes we used
it should be small. It should be big. Wait a second. It's big or small? It should be big. No, no, no. It should be small. It should be small, but because it goes to infinity, it should be small. And you're saying that I don't know even Tikhonov's theorem that it would converges solution would converges to something.
oh,
Okay.
Yeah, yes. Uh, if, I, perhaps this sigma I use this the same for all images.
Correct,
Uh,
correct. Yes.
we can if some image is bad, we can
Weight. Yeah, you can use
weight
different
this
weights.
parameter.
Yes.
Yes.
Yeah.
Mm, and as to as to diagonal, I suppose that in Fourier transform, the matrix sigma was diagonal.
Yeah, but something what I don't like, you cannot divide by matrix. I mean, at least for me. I
Uh,
understand it's probably better to write to -1 because it's inverse and then
oh,
apply.
It is
uh, I
bilinear form
uh,
in
I
denominator.
Yeah, it's sloppy notation. I guess it's a sloppy notation. But Professor, I don't understand. It's on the left or on the right? It should be for solution uh,
But
least
it is
square.
just a number. In denominator, we have just a real number.
Yes, I assume that after before in the frequency domain, the matrix X becomes diagonal, and we divide on the diagonal element of the
Okay,
matrix
now
sigma X.
now I got. Okay, but if it's zero, it should be zero somewhere.
Yes, it should. Yes, if uh, actually. mm, Uh, Actually, we use some zeros to uh, if if um,
Okay. I see. So you actually use what is a proper mathematical word? Like Fred Golm separate. I mean, null space. You push your null space into regularization. What on the left in your equation? It just after change of coordinate, it's only vectors.
yeah,
Yeah. Okay.
yes,
Got it.
yes, and uh, uh, the and here the set C has k square elements at most.
Mhm. Now, final Sergey question we discussed with Professor Kugel. So, I mean, it looks like it's convex optimization. Am I wrong? I mean, you're getting some equations, linear or what, but I don't understand. It's what kind of optimization?
Here
Pretend they are convex, right?
uh,
Or I'm completely wrong.
excuse me, which where is the optimization is here or in previous slide?
I'm talking about the initial Tikhonov's regularization problem.
Ah,
It looks
the-
like it's convex optimization. After that, you're doing all that magic with linear algebra, splitting your
yes.
equation and so on. But
Ah,
it's still convex.
this is quadratic optimization,
Yes, it's quadratic optimization. Right, right.
and
So, yeah.
this is I try to write um, um, groups of. Mm, No,
should be some
separated.
name for your equation. I forgot how it's called. I mean, it should be some name in convex optimization for solution of the. Okay.
Just points
Weighted
where
squares. Weighted
Yeah,
squares.
no, besides that, it's weightedly squares, it's weighted with degeneration. So he's splitting null space and
yeah
image space somehow in a very smart way, I guess.
uh, yes, I split it. These are a set of linear equations of size k times k at most,
Correct, correct. That part I can see.
and this oops,
So okay, what is the order? 10,
oh
100?
k might be 2, 3, 4 at most.
Ah, okay, okay.
Perhaps. And
Okay, K equals 2. Let's check.
yes, okay, and
Oh, so Nyquist give you constraints.
oh
Is
yeah.
that prefer? Ah. So you are fixing cutoff frequency just in advance by 1/2. Okay, I have to think about it. Okay. Yeah.
Yes. Uh, these inequalities determine whether we take here plus 1/2 or minus 1/2.
Mm-hmm.
Mm. And and thus we resolve, and thus we construct the image with resolution which is k times in this case which is uh, twice finer on over each coordinate.
So like optimization for constraints, it would grow with number of k, and that's it, I believe. Only by number of k. Here it's how many you need boundary conditions to check. Like 4, right? Almost 4. Yeah, 4. But when it's let's say k equals 4, it would be how many? I don't know. Yeah,
And what is written in denominator? This
16.
sigma x is a matrix, yes?
Oh, sigma x is a matrix, and but here we
Numbers.
yes we
You need
assume that
to come up with better. It's
yes
sloppy. I mean, I understand, but what he's saying, Professor Kukush, that at first he takes diagonal form and everything else like zero or those eigenvalues, and then he divides just by some eigenvalues of his. Uh, what is the dimension of your matrix, Sergiy? How many of those equations you have? You have 16, right? No, I'm. What is dimension of your sigma x?
well
The
sigma
diagonal
x
matrix.
in this case sigma x is twice nx times twice ny.
Correct.
It
So
is very
it
big.
would be 6. Yeah. Okay.
It is very big.
Okay.
But
So,
I assume that if we go to the frequency domain, that this matrix becomes diagonal and divide by the diagonal element only in frequency domain.
okay. What is the dimension of x hat and what is dimension of x? Whatever it means.
Oh, x x is in this case. Well, sorry.
For
This is x twice an x times twice an x if k is equal to 2. And the x hat is a Fourier transform of x.
so it should be. Let's go back to that equations. You have 16. How many? You have 16 equations, right?
Excuse me.
Let's go. Yeah,
Oh,
like
we
here,
have
you have how many you have equations? You have 16 equations. For
oh,
each equation, you have only one number, what you call to divide that big sigma of x, theta x, theta y, correct? For each equation, it's just one number. What I'm trying to say.
for each
For each equation, what is in denominator? Let's think about. We have 16 equations. This is just a number for each equation. Am I right?
we have after after separation we have 4 equations with
Yeah, it's
4
some
unknown
complex
variables.
expression. Let's forget about it right now. I'm just asking about first term. It's just
Yes.
number. That's why you divide by that number of corresponding its eigenvalue for some metric.
Yes.
For each equation, denominator or in the first term, it's just a number, right? We
Yes.
have
Yes.
we have
Yes, it
16
is.
equations, and that's why you put such notation. But it should be something, yeah. Okay.
It is. It is.
And why that number is positive, by the way? Why it's positive? I don't understand. Why it's positive?
Well, because it is. Oh, it must. It may be. It is non-negative. But because it is eigenvalue of
Is
a
it true?
positive
You're saying
semi-definite
that
matrix.
it's just symmetric positive? I don't understand.
It is
Why?
either zero or positive number, but we cancel out the
Okay. We are remove. Okay,
zero.
okay. No. Everything is fine. Everything is fine. Because zeros, he assumes that he can get rid of them. Okay.
Well, if some of them are zeros, we remove the equations and we set the corresponding frequencies at x to be 0.
What is the meaning of that?
Oh,
Okay,
well,
okay.
let's say if sigma is
Oh my God.
if
You
if
have it also in the second term. You have it in the second term.
mm, um,
As constraint. No.
I'm
Uh,
sorry.
yeah, you have it as constraint that it should be bigger than 0. Okay.
Sergey, you have maximum 10 minutes, not
Okay.
more.
Yes. Yes. Perhaps may I say what I try to do if we have if shifts are what different on the field of the image, and I try to the following. If I have a big image, if images are very big and shifts between images are uh, different
Mm-hmm.
um, in different parts of the image. First, I try to uh, estimate. First, I try to separate this all these framed pictures into 4 quarters and estimate shifts in each of these 4 quarters. Then I interpolate the shifts. Then I perform some averaging.
What is linearized homography? Can you give an
Oh,
idea?
oh yes. Um, uh, uh, Homography transform is a transform of the space which maps lines into lines and which maps conic sections into conic sections.
Mm-hmm, mm-hmm, mm-hmm.
However, I try to do with very uh, small homography which shifts each point very little. And
Okay, it's something like that famous statistician did, Grenander.
Grenander.
Grenander, yeah. So he did something similar. Okay. Sorry, Sergey, use the most, at least for me as physicist, slide before that. That part, I believe, yeah, it's complex and it's just next step. But can you go to previous slide? You're saying something important here about your work, about yeah. So can you give an idea for your problem? What is signal to noise ratio? How, I mean, is it big or it's, I mean, like for me, it's always a problem because I have a signal to noise is extremely big. I mean, or whatever. So I here it looks like anything about estimation of noise.
uh, yes, with mm, uh, I don't remember numbers
Uh-huh.
mm, for. Tikhonov optimization, it is rather easy to calculate the signal and the noise, and this is true even if the matrix, if the matrices were not well specified. If they are, if matrix sigma is wrong, but it's possible to. However, I cannot theoretically evaluate the effect.
Nobody knows how theoretically it's evaluated. I'm just trying to think if you have Gaussian window, how big is your variance? In other words, your window for which you make averaging or your kernel, the size. It's how many like pixels altogether? 10 by 10, 5 by 5, or it's 50 by 50? What do you think? Does it make sense even what I'm asking?
Oh,
Maybe I'm not.
perhaps perhaps because this solution images, because of separation,
Mhm.
uh, I managed to, at least computationally, do it with several hundreds.
Okay, okay. So it's
But,
yeah. It gives you
but
an idea that noise you are able to handle that small noise, but a small size of the pixels, so 100 by 100. It's great, I believe, at least
oh,
for me.
I'm sorry, I did not make. I did not make 100 more detailed image in my in my the coefficients k was 4 at most. The coefficients k was
Yeah, no. That part I understand. But nx times ny,
yes, they can
you
be very
yeah,
big. Yes,
yeah,
maybe perhaps.
few thousand, 10,000.
Oh,
Yeah.
yeah. Well, I it worked with half thousand. It worked with 10,000. It,
Okay.
I tried to
Uh,
do.
can you show a picture how it
Yeah.
works
Oh,
at the very end somehow?
well,
Yeah.
perhaps.
Do you have a picture? Some
Yeah. Just some experiment.
some
It would
10
be
bad
great.
pictures and one good picture as a result. Or
Just while Sergey is before the fascinating talk, I checked. I played for a long time, for 3 years, with so-called computer and make images. And it's kind of funny. Once yeah, I asked show handshake of Putin with mask. So it produced me a picture, but because of diffusion, mask, it was mask, but he looked like that Chinese C guy with some features.
Well,
Diffusion is
yeah.
I'll send
well.
yeah, to just it was funny. It's but I did, yeah. Oh.
Yes. However, these images were made by
Satellite,
contributor
satellite.
by Artur
Oh,
Lysenko was made.
so it's synthetic data. It's not from satellites. It's
I
a
think it was from satellite. I think I
okay.
have to check.
Yeah. No. It looks like it's yeah. Uh,
So, and
so
where is
what is red arrow? What is red arrow? It's
It is well. I try to maximize.
uh-huh.
This is a small fragment, and this is fragment magnified.
Ah, so you're cleaning with, and what is it supposedly? Some enemies deep or what? What is it? I'm just curious.
Oh, I think it could be.
Whatever, it
Well,
could be many things in this world nowadays. Yeah.
this seems to be some uh, town or city, and this where is cursor? There's a railway station on the image.
Oh, okay.
But
Excellent. Yeah, it's yeah. I just want to say that you know, I've been doing it for many years, but what I want to say is that with this presentation we have to understand that it's so many difficult both mathematical and applied mathematical concepts. So yeah, it's just fascinating, Sergey, your approach. Yeah.
Sergey, thank you for your talk. And we
and
have some experts in image processing here, but maybe Kuzmenko is present here from National Aviation University. And
Oh, okay.
maybe
Hello.
Natalia, can you,
Yes.
yes.
Hello, dear colleagues, and I would like to say many thanks to Sergey for such a very powerful and interesting presentation. It was really a great job, and I think it has a real application that are very necessary today in different application fields. And if it is possible, I have a small question to Sergey. Sergey, how do you think, is it possible to apply your proposed approach for video stream processing, not only for images, but for video? Since video basically is a continuous set of images, right? So is it possible to apply your approach for video processing? Thank you so much.
thank you again for your attention. Thank you. And I'm sorry for poor connection.
So, Sergey, can you say something about video file, video images? Can you apply your approach to video?
Well, I think that actually I did not. I try to apply use this for video images for testing, but I faced the problem that with cheap camera, the video was itself underwent some processing. It was not so.
Yeah, and if I may give my vision, because I was doing something. yes, it's possible, but remember when we have video, there is a problem. If you want to have Fourier transformation, what Sergiy did, you need for all moving those frames in dynamics, you have to keep all information about your Fourier transform. So directly, it requires some different, I would say, basis with what Sergiy did. We need to use what is called wavelets, because wavelets, they do localization both in time and frequency. In other words, like all of you know JPEG pictures, right? And there is also that format GMP, I mean, for videos. So for videos, even to compress video, people, they use wavelets, and there, it's if you have wavelet, you do not need to all the time to recalculate that person is going near his garage, and you need just to keep separately his movement from the whole picture. And I believe it's a long story, but the idea of regularization, how Sergiy had it, yes, but remember that it's another problem, like I mentioned, diffusion. People who would do such, it's called space scale approach. My God, I mean, it's definitely over my level, because they use for stability backward Kolmogorov equation. They would follow forward. It's yeah, but it's definitely the Sergey's idea. It should be just somehow to convert it into wavelets. It's just my kind of opinion. Thank you.
Okay, thank you for discussion. And any other questions? If not, then we finish our fascinating talk and topic.
Yeah, the sense, Sergey. Yeah, I mean, at least it's true. Remember, I'm not a mathematician, not anymore. So as applied mathematician, it was yeah, so many different things. Yeah.
And
Okay.
Sergey, is it published elsewhere, or can you give a reference or whatever? No. As far as I know, they submitted a paper about this stuff. We will
Okay.
wait for publication, at least.
Yeah. Okay. Thank you. Thank
Uh,
you, everybody. And yeah.
Thank you everyone for invitation and for such a powerful conversation. Thank you so much.
Thanks,
Yes.
Natalia. Thanks.
We have to finish our session. And
Yeah,
next time, a Hungarian mathematician will give a talk
it should
from
be interesting,
Debrecen.
definitely. Yeah.
Yes,
So please
from
invite me too.
Debrecen. Okay.
So thank
That's,
you and have a good evening.
Yes,
yeah.
goodbye.
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 Goodbye, everyone.
Goodbye. So, goodbye to all.